All right, hell yeah. So we're reading textbooks. This is beam bending. This is section 5.2. So let's go to the beginning of this book. We got material mechanics, James M. Gear. Hell yeah. So 371. And booyah. So let's check this out. So I'm just going to read the text, and then we're going to kind of explain what's going on. This is good. I think it's a good skill for me. And then also, as a viewer, you know what I mean? Not to have a lot of visuals, not to have a lot of things written down. I kind of just use my cursor on the side. And because when you're reading textbooks, you know what I mean? It's a good skill to have those imagined things in your head. So hell yeah, let's do it. When analyzing beams, it is often necessary to distinguish between pure bending and non-uniform bending. So this section is 5.2, pure bending and non-uniform bending. So let me see if I got this right. So pure bending is where you just have a moment that's causing the bending. So if you had a flexible ruler, applying a moment at this point and at point A and B would be like taking two fingers, on each hand, and then applying an upward and downward, basically a moment. A moment is always like a force in two opposing forces separated by a distance. And I think I kind of got the directions wrong. So if this moment goes this way, I'm going to have a downward force right here and then an upward force right there. That's going to cause this type of rotation. Cool. And then the same over here. And that is going to be different than what we talked about in section 2.1, just a cantilever and a force up. Here you're going to have shear forces and bending moments. So for our derivation, we have to start with just pure bending. All right, let's see what the text says. So pure bending refers to flexure of a beam under a constant bending moment. Cool, so that's what we said. So I think this is a very useful thing to go over textbooks because every sentence is very truthful in nature. It's very well thought out, and it has a lot behind it. You know what I mean? Even just one sentence can be like a whole chapter, previous chapter. Sweet. All right, so therefore pure bending occurs only in regions of a beam where the shear force is zero. Cool. So this also, you can set up this scenario even if you have a flexible ruler. And, if you have a flexible ruler, to get pure bending as close as possible, like over here, I would apply a downward force probably right here with my finger, and then an upward force supporting like right here. And then so that would generate a couple right here. But in between my finger at this very end at point A and then my other finger on the top pushing down at this point right here, I'm going to get a shear force to develop in that region. And so that's a good practice problem. And when it comes to internal forces. And the same thing here. If I actually bend a flexible ruler with my hand and two fingers, I'm going to push down with one finger right there, and then I'm going to support or push up with the same force upward right there. And that distance between my two fingers, I'm trying to get them as close as possible. I'm trying to simulate a pure bending as close as possible, but there still is going to be a distance between here, and I'm going to develop a shear force. But the cool thing about that scenario is that there won't be any shear force from the edge of this finger all the way through the beam to the edge of that finger. So that is simulating a moment, like kind of pure bending. You know what I mean? It's not going to be pure bending between, again, from there to there, where the applied loads are applied. But I just want to say, this is very useful to me, and I kind of just came up with it. It's just kind of that aha moment this month was just like, hey, a pure moment like this, if you see a curved line and that's indicating a moment, it doesn't exist. You know what I mean? You can't apply a moment at a point. Theoretically, it would be impossible because a moment is two opposing forces separated by some distance. So it's very useful. And this is where I messed up on the other day I said, oh yeah, this moment would be an outward force this way and then an inward force that way. It's like, no, like if we say that this is the moment, then if I could apply a force at the top of this beam right there, and I could apply it this direction, and then I could go to the bottom of this corner and then apply a force this direction. And then so that would cause this to rotate that way, and that would be similar to this moment. And so the other direction I could do it is a downward force right here, and then an upward force right there. Just get them fairly close together, and that would simulate as close as possible as a pure moment. But I just wanted to bring in that scenario because you will generate no shear forces if you do that from the outside or inside of that the applied loads. So again, if I apply a load there and there, the shear forces will be zero all through here, and you'll just have the resultant moment. So that's going to be what this second sentence is. Therefore, pure bending occurs only in regions of a beam where the shear force is zero. So you can have a beam where there's shear forces in other places, but you might have a region where the shear force is zero. So then this derivation applies. Cool. And we're going to get a differential equation. So let's read this all the way through. Therefore, pure bending occurs only in regions of a beam where the shear force is zero, because the shear force is equal to the change in momentum. The change in the moment. So the change in the moment. So the definition of a shear force. If I have a shear force, then the moment at this point, like if I cut this beam open right here, if I have a shear force, it means that the moment over here in internal slice is going to be different than the moment right here. I guess we're not going to go over that, but we could. Like, this is where you want to go. Equation 4-6, well, let's do it. So we're going to go to chapter 4. It's always good to, so there it is. So those pictures. And so what this is saying is that if I have any sort of shear force, so in all three of these diagrams, I have a shear force. And in all three of these diagrams, guess what's going to happen? The moment on this side is going to be different than the moment on that side. And in all scenarios, and these are a differential slice, so this distance becomes almost zero. And if that's the case, then there's hardly going to be any change between this shear force and this shear force. And so you hardly get any change in moment, but you still get a change in moment over here. As you can say that this little slice goes to zero, you could say that the moment is the same. So in this, you get continuity. If you're drawing the moment equation, it's going to appear at this point to be the same on this side as to be the same on that side. But it's going to have a slope to it, you know what I mean? So you're going to have continuity, but it's going to be slightly different. Where over here, you're going to get a drastic change in the moment. So if I have an applied load, then this moment is this shear plus this applied load. And that's going to be this, this half distance away. So this is not a differential term. But still, in general, if you have any shear force, if you have this or this, that's a known quantity, you are going to get a difference in moment. So back up here, it's just a differential difference. It's hardly any. Here is going to be a definite difference in moment. And I forget if this is where like the graph isn't discontinuous. Here the moment diagram is discontinuous. You're going to have like maybe a moment here, and then I'm just going to jump up to a new value. So I'm going to have this m right here, and then I'm immediately over here going to jump to this new value. It looks like we do the same thing here. I'd have to go back and do these derivations. So that shows my lack, but at least I spent some time on this month. And it's kind of cool to actually talk your way through it and be like, no, there's some asterisks and some red flags. Like, I have to go back and be like, you know what I mean? Is this moment discontinuous? Or does it just change slope? I think one of them just changes slope. One of them is a continuous line. All right, booyah. So let's go back. 374. 370. Hell yeah. All right, so that's that differential equation. Sweet. So in contrast, non-uniform bending, that's going to be what we just saw. Those three diagrams were non-uniform bending. There was some aspect of shear force in the internal cuts. Cool. Refers to flexure in the presence of shear force, which means that the bending moment changes as we move along the axis of the beam. All right, hell yeah. So, you know what I mean? And that should just scream like, hey, if we have that going on, you know what I mean? Maybe we take an integral approach to figure out what are we trying to find? Like, what's the whole purpose of this chapter? The whole purpose of this chapter is to, when we apply this moment, we get a curved shape. So I'm just going to bust ahead. So we get this. So when we apply this moment, we get a curved shape. And that means that we crunch in the top, we stretch out the bottom. So in my previous videos, the two ways to look at this is that materials can only change length so much before we consider themselves failed or past their allowable, what we designed them for, which both of those can be like, hey, a failure. You know, if it's past the allowable, you might lose your job. So that seems like, you know, something, even if something didn't catastrophically fail, maybe the deformation, now the bridge is all bent up and now it's visibly like, whoa, maybe we can't use it no more. That would be a lucky scenario. Usually things just fail catastrophically. Okay, so there's two different ways. Material mechanics is always like, hey, things can only lengthen so much, and that percentage is tiny. For steel, it's 0.2%, so it's good to rattle this number in your head of 0.002. So I'm going to hopefully go over this just in a couple sentences. If I have something that's a length of 1 meter or 1,000 millimeters, I can lengthen it to 1,002 millimeters. That can be its new length. And then after that's the point where we considered it failed. I can also crunch it in to 998 millimeters. That's as much as I can crunch it in. That's going to be failed. And so just due to like total geometry of this beam, if this is a 1 meter chunk, and the beam is just hella huge, you know what I mean, 1 meter in height, I can measure from here to here, and that length better not change by 2 millimeters. It better not crunch in by 2 millimeters, and here it better not lengthen. But if it does, I mean, if this crunches and this lengthens, I'm going to get some sort of angle, and that's due to this moment. And we've talked about, well, I talk about how if you consider this little square to be four atoms of iron, 4 iron atoms, a moment, again, is 2 forces. One force will be up this direction, and one force will be that direction. Those 2 opposing forces will apply the moment, and I can take this moment and place it right there. And so I have 2 forces crunching in these 2 atoms, 2 forces stretching those. And so what we get is a change in angle, and those are going to be little, like this kind of shape, trapezoid. And every adjacent, 4 atoms will also have the same shape, and so you will get a smooth curve. All right, so I started this by talking about the 2 different ways we can recognize like what this chapter is about. And this chapter isn't even about, it's using the change in length, which is called strain, which I think is less, it gets brushed under the rug because we typically like to talk about things in the pressures that are getting generated. And normal pressures, pressures in compression and tension, those are very similar to taking, like going in a submarine down into the ocean, taking a rocket ship into the vacuum of space. Whether the pressure is getting reduced or getting extreme, those are synonymous with axial forces. So you're going to get crunching here and then tension here. Okay, so that's this chapter. This chapter is to get a number on this tension and the number on this compression. And in the middle, we're not going to have any change in length. So it's going to be 0 tension, 0 compression. Like, it's literally like those molecules have no idea what's even happening. And I think that's kind of cool. It's good to personify things. You know what I mean? Consider every molecule as like, you know, a little, I don't know. I was just thinking, like, you could even, you know what I mean? When you do like a cut, you can just imagine you are the cut. Like, you are trying to hold this, you know, piece. That can be useful, especially with like cantilevers at a wall. You're like, well, what, you know what I mean? So anyway, yeah, we're trying to find the numbers on the pressures, which are called stresses. So those stresses are the Greek letter sigma, and it's in PSI. It's in, and I got to get better at using the metric, because probably 99% of my audience doesn't use or doesn't want to use pounds per square inch. So in the comments, always say that. Be like, nah, like none of us, I don't know. I'll try to just do both. But hell yeah. So you get pressures in pascals. That's a Newton per meter, which is a quarter pound over a full meter. It's like 2 sheets of newspaper. It's low pressure. Compared to 1 PSI, like 1 pound over a square inch is just like, dang. Yeah, that's substantial. Yeah, that's like, I don't know. It'd be like taking a pint glass filled, taking a couple quarters underneath the pint glass and then putting it on your arm. That might be a good indication of maybe close enough to be like, what's 1 PSI going to feel like on your skin? So not terribly that big of a deal. But if you keep applying those 1 pound over, you know what I mean? If you have to hold 8 pounds, I mean, if you have that constant pressure on your body, yeah, even just 1 PSI is pretty substantial compared to 1 Pascal. All right, so where are we? So anyway, we are talking about, where did we get? Non-uniform bending. In contrast, non-uniform bending is the presence of those shear forces, which means that the bending moments will change as we move along the axis of the beam. Cool. So as an example of pier bending, consider a simple beam AB loaded with these 2 couples, and we've already explained that. And we've explained how you can like visualize these as 2 opposing forces separated by a little bit of a distance. Cool, and those are the 2 couples M1, and they're going to be the same magnitude. Having the same magnitude but acting in opposite directions. Cool, and this is what we, sign convention-wise, if I'm on this side and I put a moment this way, on this side, put a moment this way, it's going to cause it to smiley face. So hopefully you have that visualized. You know what I mean? You can, if this was your right hand, like these would be your fingertips coming over and then you know, really twisting. I don't know. It's like I think you can kind of see that. It's good to just visualize that in your head. Like grip this flexible ruler and make it smiley face. If the arrows were the opposite, you would be making it frowny face. So these are both indicative of what we consider positive moments. All right, hell yeah. And so these loads produce a constant bending moment. Now we're just going to call this bending moment M. So this is the magnitude of that. If this was a graph of the bending moment, here's its value, M1. And we're just going to say M is synonymous with M1. And that's going to be throughout the length of the beam. And there's going to be no shear forces. So the shear diagram is just a flat line at 0. Cool. As shown, you know, and this is as shown by the bending moment diagram in part B. So that's what we were talking about of that figure. So note that the shear force V is 0. So we already talked about that. So it's kind of cool to kind of stay one step ahead of textbooks. You know what I mean? But I've already kind of read through here. We've done some problems. So we kind of know. But that's just how dense textbooks are. It's like every sentence is very specific and important. All right. So that shear force is 0 across all cross sections of the beam. Okay. Another illustration of pier bending. We're going to be now talking about a cantilever. Is figure 5.3a. So 5.3, this is what we're looking at. Cantilever beam and pier bending. where the moment, so we're going to figure out that the moment is now a negative m2. And so if here's our axis, so we're going to say this is the y-axis, this is the x-axis. Our moment is going to be a negative number, and it's going to be a horizontal line indicating a constant moment. But now, is this going to make sense? Like if I apply a moment this direction on this side, let's just say this, we don't know what's happening over here, but I am applying this. This is the applied load. This is actually an internal load, where up here, like, hey, this is an applied load. And I think, like, I don't think I would have graduated by not calling a moment a load. Load sounds like a force. I don't know why I just made those synonymous, but now we're talking how a moment, well, theoretically it can't act at a point. It has to, the definition of a moment is the moment of a force. It's in the name. It's the first moment of a force. It's two opposing forces separated by the distance. Now that's one type of moment. That's a couple. Or you could just have a force, separated by a distance. But when we have a pure moment like this, drawn with this arrow, we are indicating a couple, where we have two opposing forces, equal and opposite, equal in magnitude, opposite in direction, separated by a distance. All right, booyah. So here is the applied load. And hopefully I'm saying that. If I'm not, I'll change in the next few months or whatever. But hell yeah, you got applied load over here. This is an we have no applied load over here. But this is an internal reaction. We talked about that in detail in kind of the last video. Do a free body diagram. Always take this thing and put it into outer space. I'm just going to put it right here, but I'm going to pretend it's floating in outer space. And then right here, I'm going to put a downward force and an upward force. I'm going to put this moment, and it's going to cause this beam. And if it's just floating there in outer space, well, hell yeah, it's just going to actually rotate now. But we come back to Earth and we see that this thing is static, it's not moving. So we go back to outer space, and there must be something that keeps it from moving. And this is where I show you, go back to your diagram, there is just air surrounding this beam from here to there, and then from here to here. So we can't have any just magical forces just appear between A and B. So the only place forces can exist are where we cut this at the wall. So that's the definition of an internal force. Now, when we do this, when we cut this at the wall, we're treating this as a reaction. And I got to get better with my terminology. Like this moment with a line through it, I think is the definition of like, hey, the reaction at A, which is different than then, coming to a slice and slicing a segment of this beam and then finding the internal components of it. But I would imagine, definitionally, this reaction has to be if you cut, and it's really good to get better at visualize. Like even like right now, it's like, why am I struggling at this? Because typically I want to find the reactions. That's kind of we can find this moment. And if we go back to our beam in outer space, if I'm applying this moment over here, I come over here. This moment is two vertical forces. So there's no resultant force. There's no like, hey, this resultant force is causing it to travel across the universe this way. No, our beam in outer space just has a downward and upward, equal in magnitude, opposite in direction. And so, but it is causing a twisting. So I come over here to the reaction. I can't just apply a downward force because now that would be a net downward force, and this beam in outer space would be traveling this way. So I must have to put a downward and an upward force that are equal and opposite. And so you get to the point where it's just like, well, it looks like I'm just going to apply that same moment, but just in the opposite direction. And so that's what we have. So this diagram, as long as you can mentally just remove this connection, it is a free body diagram. You know what I mean? This beam is just floating in outer space. I'm applying this load, and I must have to apply this load, which is an indication of an an internal force, but it's the internal right at the very edge of this beam. So then it's very common to cut up this beam some more. So we would just take a small little slice here and then place that in outer space. And then we come back to Earth and be like, well, do we know any of the forces on there? Yes, on this side we have this moment that's causing it to rotate this way. And then the only other place that we can prevent that is where we cut it right here. So then if this moment rotates it this way, I have to have a moment that rotates it the other way. Those are going to be an equal and opposite. And if we come down here to our cut, heck yeah, that moment's going to be right there. And we could do so. So it's very good practice, even though this is just a constant line, to, hey, like, take a cut right here. Take a cut at halfway, 3/4, and then try to take a cut at the extremes, like almost full L, 0.99 L, and then do the opposite. Come over here and take a cut at 1/100th of the length. And what you'll see is that we have this little segment. We know the force on this side is going to be a moment that way. We have to match it with a moment this way. And again, this moment can be thought of as a downward and upward force separated by a distance. And with those two forces being equal, there's no net force pulling it downward. There's no net force pushing it up. So if I have this reaction and I choose to put a load, so, even take this little small slice, if we put this moment on it, it's going to want to cause it to rotate this way. So the first thing you can think of it is just like, well, let's just apply a downward load. Cool. But this thing would be now traveling this way across the universe. So we have to apply an upward load. And then you get into the idea that we have to apply that moment. Those two forces have to be separated by a distance, and that's going to cause a rotation of that little segment. All right, booyah. And the only thing that we haven't done here is started to take cuts from this side. So it's just intuitive to kind of like, hey, reading books, I want to read from left to right. So it's just very useful. And even if I say like, hey, this is my distance x, I can still have this as my axes. I can say this is the y direction, this is the x direction. But then I'm going to come over here and take a cut. So let's visualize this. I'm going to take a cut at 3/4. So I'm going to have a quarter of the beam. And now, what is this distance to this point? Well, that distance to the point is x is equal to 3/4 L. Okay, hell yeah. So keep that in mind. And then when we have this segment, we have this moment on this side. So the same rules apply. This in the beam in outer space would be rolling this way, turning this way. So let's apply a downward force to prevent that. But now we have a net downward force. So we have to have a downward force and an upward force. So if we come back over here, this is trying to rotate this beam this direction. So I must have to have a downward force and an upward force like this to try to rotate the beam that direction. And you can see that we're applying a moment. But it is useful to be like, hey, a moment is two opposing forces separated by a distance. And again, I'll double down on this idea of a pure moment is a theoretical. I mean, it's theoretical. Anyway, so at that point, at 3/4 L, what do we have? Like this moment over here was going this way. This moment was going this way. And using your right hand, if you put your fingers in this direction and swept them this way with your right hand, your thumb would be pointing out towards us. And that's an indication of a, oh, hell no. Let's see. So, yeah, that's where sign convention, you got to be careful. Because when it comes to this moment, all we're interested in is if we're going to get a smiley face or a frowny face. So this moment, being negative, means that this beam will look like a frown. And so if we take our little slice, you know what I mean? So let me take a second. When you take this slice, you can still use, you're still using just the normal convention for like, hey, this moment over here using the right hand rule is, my thumb would be into the screen, and that would be that's a clockwise direction. That's going to be associated with a negative moment. You know what I mean? Just for all intensive purposes. And then that has to be coupled with a positive moment. So we have a negative moment, a positive moment. That's why our net moments are 0. But one is just this direction, and then the other is that direction. And those two moments have a tendency to cause a frowning face. So that's when we do our internal cut. We have to draw this in. We have to draw this in the, we should draw it in the positive direction. And then we would say, you know what I mean? If we have this little slice, we know that this moment is going that way. Cool. And then, and we're going to draw this one in positively. But, you know what I mean? This one's causing it to spin this way. A positive moment would cause it to spin more. So this moment over here has to be negative. The opposite is true. You don't have to label this in this direction either. You could just say arbitrarily, I'm going to label it in what I consider a positive direction. So I'm going to label it this way, but then I'm just going to say it's a negative value. So that is worth challenging yourself to, change up the arrows and change the sign and still come out on the other side alive. All right. Cool. And we better just get to, we're just going to do one section at a time. This is pretty good. Last section took an hour, but I need to drink some water. All right, booyah. Okay, so where are we at? Cool. So on this cantilever, we're going to... this is surprise. I didn't know this. So my bad. I didn't know that if you had a cantilever, you can apply a moment at one end, and you're still going to have no shear forces. That's pretty cool. Actually, I didn't see that one coming. So this is a pure bending situation. All right, right on. Because typically when I think of a cantilever, I think the only thing you can do to it is just put a load on the end. Even though I don't know why, and because if you took a ruler and applied 2 loads upward, well, it'd just be traveling in outer space that way. It'd just be going real fast. If you have a flexible ruler, it makes sense to be like, I can see this. I can visualize 2 moments. But when it comes to a cantilever, this new one to me, I always just thought, hey, you can just put a force on it. So it's kind of fascinating how things, even in textbooks, or the human mind just wants to ignore things. There's so much to explore and so much to learn. And at the end of the day, you're just going to use the equations anyway. Equations to get to the back of the book. Where people would want to stay 10 feet away from proofs. It's like, hell no. But then you can kind of learn stuff like this. Like, that was a new one to me. Hell yeah, if I have a cantilever welded to a steel cantilever welded to a steel beam or a steel vertical support, I can apply a moment. That would be a downward force and an upward force. You know what I mean? Trying to get this thing and, to go this way. You know what I mean? It's a little bit trickier for me to see what this would do compared to, the classic bending a ruler. So hell yeah, negative moments, this will frowny face. All right, hell yeah, we're almost done with this one. And check it out. So even some foreshadow, we talked about this. This load down, these reactions will be up. And this reaction will be the same as P. So this scenario is the same thing as taking a ruler, putting your finger there, and inducing a bending moment. And what did we say? You're going to have hella shear between here. It's going to be the magnitude of that. But between here and there, you're going to get no shear. So there you go. You get no shear. And then I guess one step ahead is you get a nice constant bending moment. And so that number will be applied in the proofs. And we'll use that number to find out how much, in this scenario, it'll smiley face, how much it crunches at the top, how much it stretches at the bottom. We first have to take a look at the change in length. This will crunch in, shorten, this will lengthen. And those numbers, if it's steel, and this is a 1 meter length, this length can't crunch in more than 2 millimeters. You know what I mean? So again, that's a good way to visualize it, because once you get to the bending stress, I think your mind just forgets all about the change in lengths. And so, so that's how we get that. We know that if this crunches in a certain amount, we can get like 2 millimeters. If this is 1 meter, then we're maxed out. So we have a compression strength if it's steel of 58,000 psi. Here we'd have a tensile strength of 58,000 psi if this was a rectangular cross section, and booyah. All right, so almost done with this little segment. And man, I don't know. I'm sure this is just not sexy. You know what I mean? Reading a textbook and not writing anything. But it's useful for me because I get carpal tunnel. Like my joints can only handle so much. Now it's like use it. There's an element of like use it before you lose it or something. But overdoing it. And I just got to be very cautious about that. So this is just so fascinating. I mean, one aspect of this is I'm going to lose my voice if I did this for more than 2 hours a day. Hell yeah. Get some more ice water. All right, so almost done with this segment. And what the hell was this segment again? You know what I mean? Pure bending versus non-uniform bending. But hell yeah, take-home point for me is like I learned that a cantilever, you can get it to purely bend. And then this last scenario is like, well, there's pure bending in between here, and so good enough. We can do our analysis between here and booyah. All right, so this said figure 5.3a, hell yeah. And that's where the cantilever beam AB is subject to a clockwise moment M2. So clockwise, keep in mind that the convention, that's where you have to like bounce back and forth between conventions. Like, this is like a clockwise moment is going to be like a negative moment. Counterclockwise is positive. But now you have to think, which side is it on? It's on this side. And so that has a tendency to make this thing frown. And so if it makes it frown, then we're going to say by this diagram, that's what we're interested in. This negative number, when we do our shear and moment diagrams, we're just focused on moments for this video, is if we have a negative, that means that visually we're going to see something frown. And that's what we see in this cantilever. Even though it starts here and frowns this way, that's still a complete frown all the way from point A to B. Sweet. All right, so there are no shear forces in this beam, and the bending moment is M, is constant throughout its length. And so they have this value of negative M2. Oh, I guess this, yeah. So this is more like, if this was a plot of like distance versus, I don't know, you know what I mean? Like this is a qualifier for this axis. Or I don't know, yeah. Sometimes I don't know what they're, why they're labeling this M, you know what I mean? When, this M should be up here on the positive axis. If this is an XY, but you're just saying the Y is the moment, you know what I mean? Like, this is a graph in the XY if this was the Y axis, the vertical axis, and this is the X axis, what we would have in the X axis is we would have the distance, literally the distance at this point from 0 to L, and in the Y direction would be the moment. And so just the fact that they put this M down here in the negative, yeah, I don't like that. I would take the time to actually draw the axes in, and then put the M up here. And then just put X over here. I don't know. But anyway, so is what they did. You know what I mean? I'm fascinated by that stuff. And that's what catches me up in textbooks. It's just like, what do they, like, what type of, well, we just need to move on. But you know what I mean? Like, what type of I don't know what you call it. Anyway, like, this is such a bummer when you just lack of words. But consistency, like what other mathematical thing would you actually just apply this M below the axes, even though you're expressing in the negative direction. I don't know. I just think it's a bizarre place to put the m. Maybe it's, yeah, anyway. So you have where, I guess, and it's almost good, like I'm going to do, the second I go back to pen and paper, it's really good to actually, put a qualifier on this. This is a moment. I would put a parentheses here, and then put an x. So this is a moment. It's the function as a function of x. Just like if you had this as your y-axis and this is your x-axis. If this is your line and this is your function, this would be y, parentheses, x, parentheses. It'd be y as a function of x. It could be f, lowercase f, parentheses, x, a function of x. You know what I mean? That's what we qualify the y-axis. So in here, it would have been way better just to throw an m parentheses x. So then you can see that this line is a function of the x direction. I vary x, I take an x value right here, and I come down and then read out the moment. Now sure, any value of x is going to be the same moment. That's what constant moments is. But that could be a useful, they should have done that. Anyway. But sometimes that is just like too much. You freak students out by putting too much notation on where it is, there is that aspect. All right, moving on, almost done. The symmetrically loaded simple beam of figure 5.4a. So now we're down to this figure. And we've already talked our way through it, so now we're just kind of, but hell yeah, you get it. Two forces down. How you would find the reactions at A, you got to do sum of the moments, you know what I mean? So you would sum the moments at point A, and you would have basically this would drive a moment, P this distance, this would drive a moment, and then you would have to couple it with an upward force at B. And what you're going to find is that this upward force has to be just the magnitude of P. You know what I mean? Because you have a downward P times A, and then you have a downward P times almost the distance minus A. And then over here you have the load. So yeah, so you can even, like, I'm visualizing this, that these two moments kind of add, these two moments, these two loads would be equivalent. If these are trying to rotate these things this way, these two loads could be replaced by just a P right here at that distance. They could be replaced by, what could they be replaced by? They could be replaced by one of these loads just right there. So I think that's surprising, because it shows you that this one's really not generating much moment. And you know what I mean? We're not taking both of these loads and putting it there. Hell no. But we're saying both of these are causing a torque, a moment, you know what I mean? It's good to do dynamics, to be like, hey, those two forces would cause this thing to rotate, you know what I mean? And start to spin and faster and faster. That's what forces do when they, cause torque. They start momentum. If this is stationary, they're going to change the velocity, and they're going to keep changing the velocity, and you're going to get faster and faster spinning. And so it's just kind of cool that both of these forces could be replaced just by one of these forces right there. So we place 1p, arrow down with a 1p right there. So that's cool. And then that's going to be what the reaction at B would be. All right, so sweet. So then we go to this graph. We're going to see that the reaction at A is indicative of this line right there. So we have positive P up. The reaction at B is this line. From there to there, that's positive P. If we follow the shear, we go at this reaction, we go up P. That shear is going to be constant, and then we go down P. We're going to have no shear in the middle. And then we're going to go from here down P, and then over. We're going to have constant shear, negative shear, and then up. So let's see, because shear is always kind of the harder one. Shear is the tendency. So we're going to take this little chunk. So let's take half of it. So we're going to take this little chunk and put it in outer space. I know that there's an upward P this direction. Due to internal loads, I know that there has to be a downward P. So just keep that in mind. And that's going to cause rotation this way. There must be a moment going the other way. And that's what we see here. We get a positive moment. But we're just worried about the shear. So we have an upward force and a downward force equal to P. And if we take that little chunk, those forces are causing a rotation, in this clockwise direction. You just have to get used to saying that's going to be a positive shear. The other way to look at it, so let's take a look at that little chunk, is that, and then I would slice it up, because that positive shear is going to happen from here to there. See how this line is always positive shear? So here's another way to look at shear is like, let's take this and pretend it's a slinky, and a slinky each of the slices would be a little bit lower. And then and that's what shear does, especially if shear is positive, you're going to have just a linear displacement. So if we did see a displacement due to the shear, it would just be kind of like exactly that scenario I just talked about with a slinky. You just have just a constant slope. Now, if your shear was varied, you know what I mean? Like if your shear was hella down to 0, well, you'd have your slinky, and that first little ring would go down a lot, and then the second ring less and less and less, and then they just would peter out. So that would have a displacement that would actually be, you could see that would be a parabol, like an x squared equation. Where here, if we have a constant shear, we do that slinky, we're going to just have a linear displacement. But that's the shear. And then here's a huge take-home point for this whole chapter is we do not... Well, so all your displacements are going to be in chapter 9. But what's going to be driving from this chapter is the fact that... So let's go back to this. I mean, we actually are scanning ahead, so we'll go over these in different videos. Is if we come back here and do our 4 molecules of iron and put a crunching force on the top 2, a stretching force on the bottom 2, cool, we get that little trapezoid, and we just do that on repeat. If we have, let's just say we have a beam that's 2 molecules high, but then it's 1 meter long, and we're constantly, crunching in the top 2, stretching out the bottom 2, making a trapezoidal shape at every 4 iron atoms. Iron's basically 98%. Steel is 98% of iron atoms. And so what we find is that property, the fact that we have those crunching in and separating, creates this angle. And on repeat, holy Toledo, we can just drastically change this angle. That's why thin 20-foot long things of steel, I mentioned like a 1-inch eighth thick. It's kind of cool. Go to your steel yard, get an 1/8 inch thick by 2-inch wide strip of 20-foot steel. They still call it plate. It's just a really thin plate. But you can just easily, when it's standing on its 2-inch vertical, you can just easily, I think, now don't quote me on this, but we could actually go through that like right now I should be like, hey, that's a good one to actually do, is just like, can I take that 20-foot length of steel and do a full circle with it, touch the 2 ends together, let it unfurl, and have everything go back to, that's the cool thing, as long as you're within that linear range and you didn't crunch the top end more than that 0.002. Every meter, this crunching in didn't become 998 millimeters. If you didn't do any of that, then every molecule goes back to the original position. I think that's the fascinating thing about material mechanics and just materials in general. How they have hella strong strength, plenty of strength to design, and you can even half that, half your loads just for safety. And yeah, you apply... Cars drive over a bridge, and then they unload, and then that bridge just magically goes back molecule for molecule to the same position, in the universe. I mean, I think that's just fascinating. All right, so yes. So we went on this tangent to show that this driving moment hella changes the angle. So, and then the other thing to visualize is like, hey, have this welded vertical. And then you can just even see from this picture, we curve up quite a bit. But if we go back to the shear forces, those shear forces just don't cause much deformation. They like that angle that you will see in the downward direction, negligible. And I haven't run the numbers. Just chapter 9 says it's negligible. I don't know if it's a factor of, if it doesn't even change 3 decimals, or if it changes the second decimal, or if it, if it's 1%, is it 0.5% change if you take into account some of the shear forces changing. But that is a huge take-home point for this chapter, is that we are taking this moment, and this is the driving. And this chapter doesn't even cover deflections. It just says, hey, when we get that crunched shape on top and length shape on bottom, we can know what the pressures are. And those pressures will get a number, and we just want to make sure those numbers are smaller than the actual pressure that steel can take. 58,000 pounds in compression. That's going to be a negative 58,000 pounds. That's what we call compression. Or a tension, a positive 58,000 pounds. All right, booyah. So yeah, that is a huge take-home point, that even though we are having shear, this shear doesn't cause any deformation, and it doesn't even drive the strength. These I-beams, that's the other thing, you know what I mean, that actually gets hella overlooked. And this is from first chapter stuff. If I have a 1-inch bar of steel, like a 1-inch cross-section that's kind of long, I can hang a semi from it. Not a full one, you know what I mean? But it's got 58,000 pounds. A full semi would be 80,000. That's a good reference. So for sure a half a semi, or like an empty semi, you could hang it. You could hang the semi truck and trailer empty from a 1-inch chunk of steel and be very happy about it. Materials are strong. Cool. And then also you could put that semi-vertical, and try to get all its pressure up against and then weld that 1-inch, bar to a wall. Have a cantilever sticking out, and try to place all the way to the semi right there. Now, we're not going to place it out here because that's the whole idea of this chapter. That's bending, and we just know bending is weak. Hopefully you have that concept. And that's good to explain right now, because if you don't understand that, it's just like, yeah, there's this tendency for things to be like, yeah, that's going to bend and break, right? But if we're able to take all that load of the semi and then just put it right there, you know what I mean? Well, it's just like, well, it doesn't seem like it's going to bend. No, it's going to shear. And so shear is only half as strong, you know what I mean? So you're not going to get 58,000. You're going to get half that, 29. So maybe we could take that semi and break through. Maybe it's a strong enough steel where it actually holds. But that's a hell of a lot of force in shear right there. When it comes to these loads on these beams, and so that's 29,000 pounds. It's 50. What were we talking about? 58,000 pounds. In shear we were talking about 29,000. So let's keep that number in mind. Because things are half as strong in shear, basically. So if we have 29,000 pounds on a 1-inch steel bar, we could shear through it. Or we could just barely hold on to that strength. Now, if we come over here and apply a downward load, so just pretend like this is a downward load, and this is just even a meter out. Like, how much load could we put on that before the bending part, before like this frowning, before we get so much crunching in on the bottom that the pressures get bigger than 58,000, and then the top, the pressures and tension get bigger than 58,000, and those are going to happen at the same time if this is a rectangular cross section, you know what I mean? But that's this chapter, you know what I mean? So even just that question, I should actually do that, and you should always challenge yourself with that. Be like, I wonder if I had this chunk of steel that you can visualize, in your backyard. Is like, do you have any steel chunks laying around? And I need to do more of that, you know what I mean? I can only do so much, or I'm only so I just want to keep motivated. So like this video is like hella motivating me, even though it's probably like just garbage to the actual what people expect on a YouTube platform. But hell yeah, people would love just to be like, yeah, I want to do that at some point, but it just requires me to make sure I can do it within a very short amount of motivated time. But yeah, I've got so much steel in the backyard. I've been thinking about that. It's just like, yeah, set up little scenarios where you're just like, yeah, how much, and especially bending. Bending is fascinating because you can't put much load. That's the take-home point. is like, it's 10x. It's 100x less. 10x less. You know what I mean? This goes out, and I think it's linear. Like, you know what I mean? If you have a cantilever, that's 1 foot, and then you double it, you have to half the load. You know, so if I can, so that should say it. If I can apply, well, no. Shear and moments are different. You know what I mean? There's a point where you have to. I don't need to stutter so much, but you can. Yeah. That's the equations of this chapter, is figuring out what your length is, what your moment's going to be. The moment at the point, and in this case, your moment's going to be maximum at that point A. That's where you're going to get the most crunching. Over here, you're actually going to get no crunching at all. So if I do apply a semi-load down here, it's not going to break here, here, here. It's going to break right at the wall. That's where we're going to have the most tension. These last 2 molecules hanging onto the wall will exceed 58,000, and then the molecules down there will, you know, get crunched together at negative 58,000, and they'll catastrophically fail. And if those 2 go, it'll be chain react, and you'll get a failure. And so, booyah. So I think that hopefully explains it, that bending is pretty darn weak. But we still use it. It's the best way to span and the best way to carry loads. And we just have this chapter to make sure that this is beefy enough. But that was going through the whole point of saying, yeah, the deflection's due to shear, nothing burger. And actually, if a car drove over this load P, would I just shear right through? No. You know what I mean? Because we are, I'm designing this car to actually get to the middle. And that's going to be bending. And it's going to be, I don't even know if it's 10x. It'd be kind of fascinating. And it depends on the length of this beam. But yeah, it's always a good one to do. You know what I mean? If you have the cross section of your I-beam and you have the internal area, the shear force is just the so the numbers that we're getting for crunching and tension are sigma, and those are like axial loads. Those are normal loads, and they're very synonymous, again, with putting something deep in the ocean or out in outer space. Like crunching in on something, ripping something apart, due to axial loads, due to normal loads. Now, shear is a crazy beast because it's geometry. I think it's very much associated how a moment is, like considering moments loads, or you have to kind of look at what they are. They're 2 forces separated by a distance. Like all 3 of those aspects are important, the 2 forces and the distance between them. Same thing with shear. Shear is a arbitrary value that we apply for sideways pressure. And, the pressure is on a vertical face, and that pressure is sideways to the loads applied. So it is, to me, that seems darn empirical. But there's a lot of ways to look at shear. I've done a few videos. Now, I'm not, that's my motivation. You know what I mean? To take like a very elementary and fundamental look, because they do so in this book. It seems like it just gets overlooked, a lot of those aspects, where they'll just say shear stress is a thing, but it's not synonymous with it's not synonymous with anything like liquid pressure, because you're considering it a sideways pressure. But it's still, a lot of material mechanics is like, hey, we have this value for the pressure, the sideways load, and it can only be such a big number. And that number is going to be equal to the force that you apply down, the shear force, and then the surface area of the beam itself. And that's what we're going to call an average shear force. And then later in chapter 6, and even in this chapter, is mainly the first introduction of showing that it has to be an average, because you can't have shear forces at the top. There's no shear forces at the top and bottom. And I think that should have been hella more explained in the earliest chapters of the material mechanics books, because I think I graduated without really not knowing that. And then they just it feels like they just throw it in on you. And so that's Because the earlier chapters say, hey, you just have this average shear force. And I even got, like last week, someone had a question on average shear force. And I just thought that was just like an allowable thing. You know what I mean? But no, it's the fact that you can have shear forces top and bottom, but we still have a number from an empirical standpoint that, hey, if you have a force and an area, then that means, or an area of steel, let's say your average shear force is 29,000 psi, and I have a surface area of an I-beam of, like, let's say 10 square inches. It looks like I can apply a shear force of not only 29,000, but 10 times that. So 290,000 pounds. Now, do you think I'm going to drive something over that weighs 290,000 pounds? You know what I mean? Over a bridge? No, it's not the shuttle. And so, got to get better with my jokes. All right, so, but hell yeah. So shear is always, you can, but it's fast. I was trying to look at one YouTube video where a truck drives across a bridge and it just instantly falls. Like, by the time the second wheels get past point A, that thing hits and it only drops like 4 feet into like a mud puddle. But that was hilarious, and I just couldn't find it. So hopefully I did a good job of explaining that visual, because that was failing in shear. It didn't even get to the middle. You know what I mean? So that was pretty funny. All right, hell yeah. So we have, I want to be done with this. So we just have from there to there. This symmetric. So we might be reading the different things, but we have this figure 5.4a is an example of a beam that is part in bending, part in non-uniform bending. So that brings it home. We're talking about pure bending and non-uniform bending, but check it out. You know what I mean? Max bending is where the breakage is going to occur. So in this scenario, we're going to get a break somewhere between here and here, because those crunching stresses, those tension stresses are going to get to that 58,000 if this is steel, and we're going to get some sort of rippage along the bottom and some sort of crunching tears on the top, compared to this scenario. Our max moment's going to be at A, and they should have put a moment diagram on this one. I mean, goodness. And you know what I mean? You're going to have just a linear. And let's do this one. So if I do this, I'm going to have a smiley face. That means my moment's going to be positive everywhere. That means right here I'm going to have a max. So if I drew the moment diagram, I would go up, and then I would draw a linear line all the way to 0. Because my shear force is 0, and so it's just a linear line for my, no, I messed that up. I have a constant shear force. Yeah, this one we talked about. So our shear diagram, draw it in, is going to be a constant load. And is it going to be in the positive direction? No, check this out. So like here, taking this little thing, this load is going to cause it to rotate that way. So that direction is associated with negative shear. So just always internal loads. You should use this, take this little segment, put it up here, do a little free body diagram. Your loads on this cut, it's the shear is the one that causes it to rotate counterclockwise, is the next, sorry to say it that way, but that's the negative direction. When we do the cut, it's always the shear is going to be wanting to rotate it clockwise, which seems counterintuitive. I'll make a video on that. It's very synonymous with the same thing as like, hey, if I put a moment over here and I put a moment over here, two opposing moments, but we have to say that those are both causing a smiley face. You know what I mean? So the same aspect applies with shear, and it doesn't apply in the, I can kind of foreshadow, is because if I have this little chunk, so let's just take this chunk. I think we got that visualized. I'm going to have, so here I'm going to have that downward force, and then here I'm going to have an upward force. And then let's take this chunk to be a little square, because they're going to do that on you with these shear forces and, elements. But we can take a big element. I can just take this whole element. And what's going to happen is I'm going to take that whole chunk. I'm going to have an upward force and a downward shear force. And then on this face, and then in this scenario, I'm going to have two moments that are going to be positive. Let's see. And yeah, those would balance. I don't know what I was thinking, but when you get into a scenario of pure shear, where you don't have moments on either side, I have to rack my brain for, because that's the later part of this video, is just like, what happens is you have, let's do this, you have a square, and we're going to say, let's say we have a downward shear on this side, and an upward shear on this side. So that's going to be a positive shear. It's going to go this way. That's going to be the opposite of this scenario. But then if we look at that square, we got a downward and an upward. And if it's in pure shear, there's no moments. We have to have a shear force this way and that way. And so those two shear forces are causing it to rotate the other direction. So if we're saying a downward force on the right, or a positive, so in the vertical direction, if we're saying which that's what we're doing. We're cutting this thing and we're trying to find the internal reaction, and the shear force is always going to be on that cut in the vertical direction. But when we take a little chunk of that, we're going to have a vertical force. Downward is positive on this side. Upwards is positive on that side. That's going to cause this thing to rotate that way. And if it's in pure shear, we have to have two opposing forces, one this way and then one this way. And those are going to be in this direction, which is counterclockwise. And when we're saying that those two are associated with a positive shear. So that is it's a bummer that I don't want to do this with pen and paper for a while, but it's kind of cool to visualize that, and it's better for and maybe it's just good for my understanding, because it's just like, I don't know if you can even see anything, but yeah, so that's the reason why you might have so let me phrase this, like, why wouldn't they say up is going up on this side and down on this side is positive shear? Because that would fit with the right-hand rule. Why did they not do it that way? Well, it's because you have that little element and you got those top forces that would have to be the opposite anyway. So you have this opportunity. So that's where the opportunity arises, that you can then say in the vertical direction, these two forces in the vertical are going to have a tendency to rotate it one way or the other. We're going to choose one to be positive. And then that gets us back to the moment. Because we're saying this smiley face is a positive moment, and back in the beginning of this, we've said, hey, if you have any shear force that's going to change the moment. So, and that wasn't a very good explanation, but the explanation would be, your shear force is associated with your moment, because when you know your shear force diagram and you integrate it, you get the moment diagram. And so in this scenario, it should work out. Let's try it out. That if my shear force is going to be upward on this face, so that's going to be negative. So let's draw the shear force in. So here's my shear force diagram. Is going to be negative P all the way over to this load and then up. So at the reaction, I'm going to go down negative P, over, and then up P. So then why is my moment? So my moment should be negative. So as I move across that shear, and see how that works, is that if I have this negative shear, the calculus is adding up those areas, and we are reducing the moment. So we're going to, but then that makes it seem like, well, is the moment getting negative? You know what I mean? Because we just said this is going to be a smiley face. So now here's the full story. Is that, and this is a bummer on calculus, and it's the trickiest part of calculus. When you integrate, sure, I'm going to get something that makes the moment get smaller and smaller. You know what I mean? And maybe more negative and negative. But when we integrate, so if I get this line like this, I can put that line anywhere. When we integrate, that's the constant of integration. I can put that line here. I can put that line at positive infinity or negative infinity if I wanted to. And so what we do is we go back to this reaction and say, if I'm putting this load here, the reaction over here, and this is what I did in the last video, is like, cool, let's take this, cut it into outer space. Would be the last thing we do with this video. Some more ice water. So we're going to put this beam in outer space. We're going to put this force on it upward. What we knew from Newton's second laws, again, there's just air around here, top and bottom. The only place we can put the reactions are at the cut. So I'm going to put a downward force to equal this load P. Cool. That's going to cause that thing in outer space to turn. I can't put any other forces on it because I have to have a net downward force. You know what I mean? And so I can put more forces. I can put. So what do we need? This thing's going to be rotating this way. So it seems like I need another upward force, but I have to couple it with a downward force. And so hopefully that like really it feels good to me. You know what I mean? Really showing that a moment is a load. Two forces opposing, separated by a distance. It doesn't mess with the forces in the vertical direction. And hell yeah. So then, again, this bar in outer space, someone puts a load on it up here. Think of you at point A. Like, what do I need to do? I need to pull down on that. Okay, now I'm just like spinning it in place. And so I also need to pull down, but then I also need to apply, and that's going to cause it to spin this way. So I need to apply a moment this way, which is an upward force and a downward force, separated by a little bit of a distance. So that combination will get that bar to just be totally stationary in outer space. All right, so now we can say that what moment did we put on it? This thing was going to spin this way. I had to put a moment this way. Back to our sign convention. If we draw this, a moment this way is going to be a smiley face because, and it's very simple to do. If I have a moment going curling this way, put the same thing on the other side, and yep, that's going to make a smiling face. That's going to be a positive moment. That's going to be on our diagram associated with a positive moment. So our moment diagram, so our shear diagram is negative P over up. Our moment diagram is going to be starting with our moment, which is a positive moment. And that's P times L. So this one's fairly simple. So we go up PL. And then using calculus, we come back to our shear diagram and be like, hey, these little areas are negative. So our moment's going to decrease linearly all the way till we get to this point. And at this point, there's no moment because it's a straight line. This picture I've said in the last video is a little bit, this right through here should show you the largest change in the curve. You know, because that's where our largest moment is. It doesn't look like it. It looks like this is straight. It looks like all the curve is in here. I think it's either poorly drawn or our eyes are tricking us. But hell yeah, the biggest change in angle because of the biggest moments here, and then we peter out to a linear. This section is very linear right there. Okay, hell yeah. So that's why we have a positive moment that goes downward, and booyah. And so that was definitely going over chapter 4 stuff, internal reactions. And I need to read the next part of like where were we at on that? We were basically just kind of done with this in the end. We were talking about that. So there's a reason I went to there. So the center region of the beam is in pure bending because the shear force is 0 and the bending moment is constant. The parts of the beams near the end are in non-uniform bending because shear forces are present and the bending moments vary. Okay, hell yeah. So again, that was just kind of a thorough way to go over. Oh yeah, I just said, hey, this should have had a moment diagram and a shear diagram because that was another red flag on mine. I was just like, it should have. For a second there, I was just like, yeah, there's no shear in this, but no, hell yeah, there's shear and then there's moment. And because again, the shear is a constant. The moment is a linear function. But the hardest thing actually is to see that the shear is a negative quantity and then the moment starts at a positive quantity because when we integrate, we can put that line anywhere. And then we have to go back and find our, what makes sense to what we are observing. And we go positive and then we drop negative because the area under that shear. And that kind of rounds it out. That shows you that presence of shear changes the moment. The moment started out positive, and then as it moved, there was always shear. And then that moment always changed. So if you had a positive shear, that moment would increase. Okay, so that is a good place to kind of bring it to a close. We're going to read down here. Did I read everything up here? Let's read this again. The parts of the beam near the end are in non-uniform bending because of the presence of shear. We have a constant shear. We're going to get a linear change in moment. So there you go. Hell yeah. And we have a positive shear. Based on those conventions, our moment is going to increase positively. And so that goes back. If you really want to, I'm going to fly back because this was extremely helpful for me. Even if these just don't make sense, run through them. You know what I mean? Even if you can't get everything about these 3 diagrams. I think the trickiest thing is, like, why don't you call this DM as well? You know what I mean? A change in momentum. It's just because it's an actual, this when dx is approaching 0, this is also approaching 0. But in this case, as dx approaches a very small wedge, it don't matter. This is actually, you're adding a legit value. So that comes up in differentiation. That is difficult. It's difficult to see that. And it's difficult to get this equation, and then they're just like, yeah, this is 0. Like dx, anything that has dx in it's basically 0, and these dv's, dm's are 0. You know what I mean? So this moment is equal to this moment. This shear force is equal to that shear force as we approach. That means that's kind of, today someone said the fundamental theorem of calculus. It is like the dumbest thing. It's just continuity. You know what I mean? The fact that, it's like, sure, there's going to be a slight change, but as these 2 parts of the graph come together, they're going to be the same value, and they're not going to sharply change. So that's where I have to go back again. One of these moments, the moment just like sharply changes. Well, yeah, I can do it. If you have a beam and you put the load in the middle, the moment's going to be 0 at the end, max at the top, but then it changes down. So you have it's not continuity, but the moment, as dx goes to 0, the moment on this side is the same as the moment on that side. So how does that work out? It's just that the slope changes. So again, if I don't have that 100% right, but here you actually get a jump in the moment. So there you go. So those are always, like, I think these are probably the hardest things to wrap your mind around, and it goes into it. So here's just kind of the three photos. I think I kind of skipped over them. Booyah. So here's the 3 photos, and then this part of the chapter goes into all 3 of those. All right, so we are going to be done with that last sentence. And so in the following 2 sections, curvature of a beam, we will investigate the strain. So that's what I was talking about. The change in lengths can only be so much. And those change in lengths are going to be 100% synonymous with the numbers of the pressures. That's Material Mechanics 101. We pull on something. There's 2 ways we know it's going to break or we're going to lose our jobs. One is we can visually see it changed length by a certain amount. You're like, uh-oh. And then the other is we can put force gauges, which most people, think that's pretty cool. Go to Amazon and get yourself some cool force gauges and start pulling heavy loads on things until they break. Get you 1 million views on YouTube. But that's the other way. But that's material mechanics. You can do things both ways. Everybody probably just thinks you just do things by pulling on things and getting this readout, this load, and then things break. But the other way to visualize it is you can only stretch something so much before, hey, looks like I lost my job today. All right, so hell yeah. So yeah, that's called strains. And again, I don't like the term stress or strain. It's the reason why I flunked out. I think I missed the first day, and by the second day I was just like, I made a horrible mistake. So isn't that lousy? Shame on me for being in a funk I think I missed the first day and actually showed up 15 minutes late to the second day. So, you know what I mean? Not much you can do on that. But some things in life, I just didn't know Some things in life require, but that teacher was the worst. He would say one thing, it would be gospel truth, and then you just move on. And he would just always use these terms, strain and stress, like you knew what the hell you were talking about. And no one did. Well, yeah, it really did. I think half the class failed. And that's a shame on that teacher. That it really is. You know what I mean? I don't get that. But anyway, that's why, hell yeah. That's why we're going to make it. We're going to make it in the engineering YouTube scene. So, booyah. All right, so hell yeah, let's keep reading. So, strains, change in length, stresses and beams, subject only to pure bending. Fortunately, we can often use the results obtained for pure bending when shear forces are present, as explained later. Yep, so that gives you it. Even though we might have shear forces in areas of the beam, it doesn't really matter. You know what I mean? Bending moment dominates. And hopefully we explained that aspect. And even in deflection in chapter 9, yeah, it's bizarre. They're just like, yeah, neglect shear forces. And it's just like, really? It's like, it's not going to change. It's not, the bridge isn't going to get lower due to all the shear forces. That's kind of fascinating to me. But yeah, all the derivations in that chapter are just moments alone. And shear and the deflections due to shear forces are negligible. And so here, yeah, we can just use this max number for our moment, and we can also find, you know, the other stresses in parts of the beam. You don't have to just find the max stress, but that's, I mean, if you're gonna, you know, throw an I-beam across a 40-foot span and you're gonna drive your car across it, well, that's the only number you're actually concerned about is that max number. Because if that max number, that's the other property of material mechanics. You pass that max number, it's very difficult to see that if I put a downward load and this smiley faces and I crunch in the top surface. I think it is difficult to see, like, why can't molecules crunch together indefinitely? You know what I mean? But I think even, that's where I want to prove, yeah, and that's where I'll just put my shoe into my mouth or whatever they say. Because when it comes to compression, things will fail in shear. And if things are failing in shear, they failed normally. You know what I mean? Because you get diamond shapes and things get ripped apart. It's actually axial tension that rips things apart in pure shear. So, I mean, just can I say that one more time? Is that if you have compression, things sometimes will fail in shear. Due to the compressive loads being too high. It failed in compression, but in a way that it was at a plane of shear. And if it failed in shear, our models show that like a little square diagonally turns into a diamond where these 2 points get farther away and it's getting ripped apart. So it actually gets ripped apart the middle. So, failure in compression can be failure in shear, which is failure in tension. And it's not too simplistic because those are sections in this book. It's simplistic in the form that I'm sure at a PhD level, when you look at materials, there's a bigger story to be told. But like my goal is to definitely shine the light or expose scenarios where I think it's just like, nah, the way you're phrasing that sounds empirical. And it's good to, it's good not to push against too many things, but that is, like, when it comes to shear, that is one thing that I'm trying to push against. And I don't mind if I'm wrong, but we'll see. But yeah, it's kind of just explore it in different ways. But, okay, hell yeah. All right, so fortunately we can use the pure bending. You know what I mean? We don't have to worry about shear forces for these derivations. All right, hell yeah. So that was section 5.2. I'm sure there's about a bajillion sections in this. You know what I mean? But hell yeah, that's the juicy part about a textbook is word for word it can be deep as hell. Because, you know, even just something like this, see equation chapter 4, you could just go on a tangent. And you should sometimes, you know what I mean? If you're just like, hell yeah, reading to here, and you got all day at the coffee shop, we'll go to chapter 4 and go through all that stuff. All right. Before this video gets awful, we're going to end it. Thanks for joining me. And guess what? That's a video.